We are back to variance. Let's practice what we've learned with some exercises. Alright, so for this exercise, imagine that you have been chosen as the backend developer or as the backend API designer for a parking application which checks for illegal parking. Alright, so I don't want you to stress about the implementation of the methods, I just want you to design the API. Okay, so for this exercise, I want you to design an invariant, covariant, and contravariant parking of things, which takes a list of things as an argument. And these things can be vehicles, such as, for example, if I define a class of vehicle, we can have bikes, we can have cars, and so on and so forth, right? So in this parking thing, I want you to have first the parameter here and also some methods. For example, I want you to have a method called park, which parks a vehicle of type T. I want you to have a method called impound, which takes a number of vehicles as a list of T. Of course, I want you to modify the API so that the compiler is happy. I also want you to have a method called check vehicles. And let's say you have some conditions as a string or as a permissions or as some kind of argument. And this returns a list of vehicles or a list of T. All right, so for the first part of the exercise, I want you to implement an invariant, covariant, and contravariant version of this API and see how these compare. Next, I want you to think about how your API would be different if we hadn't used list, the Scala's covariant list, but used someone else's API. Saying we have an invariant list of type T, right, which I'm going to provide you right now. So class I list of type T, which is invariant. Okay, so how would your API be different if you had used this API? And third, you're being a smarty pants and you want to make parking a monad. Holy dopes. So because you have your unit, which constructs a parking with the argument right in the parking class, I only want you to add a flat map method. Okay, so pause the video and think about how you would write these. Okay, this is more of an API design challenge. And compare your APIs, think about when and how each of those would make sense, or if they don't. And I'll come back with a solution and interpretation right now. So, let's think about how we would approach this. Let's start with the invariant parking because it's super easy. So let's create an iParking of type T, and this receives some vehicles of type list of T. This has a method called park, which receives a vehicle of type T, and this would turn an iParking with some vehicles into another iParking. And the implementation is going to be irrelevant for this exercise, okay? Now, impound takes vehicles as a list of T, and this returns an iParking of T because it removes these vehicles from the parking, okay? Then we have a check cars or check vehicles, which receives some conditions of type, I said string. You can pass in whatever you want. And this returns a list of T. And this is all fine. So these method signatures are all fine. Vehicles. Nice ID. Okay, so the invariant version is so boring. Let's make it covariant. So let's call this C parking of type plus T. And with the vehicles, which is of type list T. The park method is going to be the first interesting method because the vehicle of type T should turn this into a C parking of type T, but the compiler should complain at this point because this is the same situation as adding a thing to a collection, saying covariant type T occurs in contravariant position. So we will use our little hack by saying an S supertype T, so widening our type. Parking a new vehicle turns the parking of a given type into a parking of a wider type. Let's do the impounding. So def impound vehicle vehicles as a list of T. This is also going to turn this into a C parking of type T. But the compiler also complains because vehicles is a list of T, and list is covariant, so the whole type here is covariant, and that occurs in a contravariant position. So I also need to add this little type hack here, this widening of types. So this will add or impound vehicles of type S, and this will turn a C parking of type T into a C parking of type S. Although this is quite counterintuitive, it makes no sense to widen our types if we are removing elements out of our parking. But this would never occur in practice. If our covariant parking only held, for example, bikes and cars, then we could only impound bikes and cars. We would never widen our C parking beyond the types that we currently have. And finally, we have a method called check vehicles with some conditions. And this returns a list of T. And this is fine because list is covariant and it occurs in a covariant position. So this is an acceptable API. Let's do the contravariant parking with minus T. And vehicles as a list of T. And let's do all the methods in turn again. So def park vehicle is of type T, and this turns that into an X parking of type T. This is fine because our T is contravariant and it occurs in a contravariant position. So this is all well and good. Impounding, impound, takes vehicles as a list of T, and this turns into an X parking of T. This is also fine because list is covariant in the sense that it follows the variance of the type T. So if T is contravariant, then this guy is also contravariant. Okay, so this is an acceptable type, and if I compile this, the compiler should be fine. All right, and the check vehicles, this will take some conditions as a string, and it will turn into an X parking of T. Actually, into a list of T, because that's our intended API, right? So this should be return a list of T. But now the compiler starts to complain because list, as I said, is covariant, so it follows the variance of T, and T being contravariant, then this type is contravariant, and it occurs in a covariant position. So we need to run the hack again. So let's do the S, and let's restrict the type. So given some conditions, we are going to return a list of S. Now, as an interpretation of this API, first of all, the invariant parkings are, one, boring, and also very limiting because they only allow the containment of one type and only one, okay? As for covariant versus contravariant, as a general rule of thumb, and I'm going to write this here, so rule of thumb, use covariance, so use a type as covariant if you use that as a collection of things, right? So if you use a parking as a collection of vehicles, then use covariance. If by contrast you want to use the parking as a collection of actions that you want to perform on your types, use contravariance. So as a group of actions. So when you want to use actions, use contravariance. If you want a collection of things, use covariance. Okay, so both of these APIs, covariant and contravariant, might make sense depending on what you want to do. In this case, I would err on the contravariance because X parking here, the contravariant version is more used as a group of actions that you want to apply to vehicles, like parking, impounding, checking, and all that kind of stuff. Now, let's move to the next part of the exercise. What if you had to use someone else's list API, which is invariant? Well, the invariant parking would just stay the same because it's so boring that it cannot really move. All right, so our interest here focuses on covariant and the contravariant versions. So I'm just going to copy these over, and I'm just going to name them cparking2 and xparking2. And let's take the methods in turn. So if we took vehicles as an I-list of t, this is all fine. Parking a vehicle doesn't affect the API. Impounding with vehicles as an I-list, and this returns a cparking, of course, cparking2. Okay, then this should still compile fine. Now, you might be wondering, because iList is invariant, wouldn't it make sense to remove this little hack over here and just use iList t and just return a cparking2 of type t? Well, if I don't even need to recompile this again because the IDE tells me covariant type t occurs in invariant position. Now, this is new. That's because t is covariant, but iList is invariant. So we need to apply the hack again. To widen our types. Okay, and checking vehicles, if it returns an I-list of t, then it says covariant type t occurs again in invariant position. So unfortunately, this will require the same widening of types yet again. This will not affect the way that you call check vehicles, but it does affect your method signature, and it's slightly harder to read with all these new type arguments. Now, let's move to the contravariant version. So xparking2, vehicles is an I-list of t, and parking a new vehicle results in an xparking2. So this method is quite unaffected. So if I recompile this, the compiler should be fine. Okay. Now, impounding of vehicles as an I-list t should result in an xparking2 of t. But again, vehicles is an I-list t, so a contravariant type t here occurs in invariant position because I-list is invariant. Okay, so the way that we would solve that would be to apply a type restriction. So introduce the new type parameter s, which is a subtype of t, and this will return an xparking2 of s. And the check vehicles should return an I-list of s, and the type restriction here should be fine. If you remove the type restriction, then the compiler should complain, saying contravariant type t here occurs in invariant type, in an invariant position for iList. So the type restriction should be kept in place. So that was part number 2. Part number 3 is our smarty pants with flat map. So, in the invariant version, the def flat map takes another type parameter, say s, and a function from t to iParking s, and this should return an iParking s. This is totally fine. Okay? Let's copy this chunk, and let's complete that in our covariant and contravariant version. So in the covariant version, if I take a function from t to cparking s, and I'm trying to return a cparking s, then this should be fine. For the contravariant version, from t to xparking s, and this should return an x parking s, then this is not okay because the contravariant type t occurs in covariant position. Well, why is that? So we said that method arguments should be in a contravariant position. So this whole thing, t arrow x parking s, is in a contravariant position, okay? But t arrow x parking s is a function type, so this basically is function 1 from t to x parking s. Okay, so this is what it comes down to. Now, we know that function 1 is contravariant in t. That means it's in an inverse variance relationship to t, which makes this position right over here a double contravariant position, which is covariant. Yes, mind blown, I know, blame the math, but this is what it comes down to. So this position for t becomes a covariant position and the compiler complains. So to solve that, we need type restriction. So instead of s, we need another type r, which is a subtype of t, and the function here should be between r and an x parking s. Alright, so quite a mind twister. So hopefully this lesson clarifies the majority of generics related problems, and you can read now Scala APIs with different eyes now, I hope. I'm Daniel, and I'm waiting for you in the next video.